When humans describe a target object present in a 3D scene, they do not just mention the egocentric properties of its color and geometry. However, they typically describe the target object by using explicit associations between the target and other objects coexisting in the scene, known as the anchor objects. Despite this fact, current methods are constrained due to a lack of available grounding data, where these other mentioned anchor objects are not provided. In this work, we address this oversight concerning the utilization of anchor objects. We introduce ScanEnts3D, where we are collecting Phrase-to-3D-Object correspondences, also known as scan entities, for NR3D and scan-referred datasets. We share with the research community grounding annotations that go beyond each target object and explicitly provide all the correspondences between all the 3D objects and any of their mentions. In summary, the contributions of this work are the following. First, we introduce a large-scale dataset extending both NR3D and scan-referred datasets, including in total 369,000 Phrase-to-3D-Object correspondences. Second, we propose appropriate training losses exploiting the new annotations. We can significantly improve the performance of several 3D neural listening and speaking architectures. Third, we improve the state-of-the-art for neural listening in NR3D and scan-refer benchmarks by 4.3 and 5% respectively. And we improve the state-of-the-art for neural speaking with NR3D dataset per CIDR by 13.2 points. Finally, we present quantitative and qualitative results indicating that by training with ScanEnts3D dataset, different neural speaking or listening architectures not only attain improved performance, but do so in an intuitive and interpretable manner. As shown in the following table, ScanEnts3D dataset provides much more annotated objects, provides annotations for the mentioned anchor object instances, and provides non-Phrase-to-3D-Object correspondences. The collection of ScanEnts3D dataset consists of two phases. The first phase is the annotation phase, where an annotator is given an utterance and the 3D scene. The utterance describes one specific object in the 3D scene. The annotator is first asked to mark each noun entity that describe one or more specific objects, for example, table, lamp, or the couch, in the utterance, and then the annotator must highlight the corresponding 3D objects in the given 3D scene. The annotator can zoom, pan, or rotate the 3D scene to find the corresponding 3D objects. The second phase in the data collection is the review phase, where a reviewer is given one annotated example randomly and is asked to determine whether the example was correctly annotated by checking every entity, and if the example was annotated incorrectly, the reviewer is then requested to correct and fix the annotation. We propose modifications to several existing state-of-the-art architectures so that they can utilize the additional annotations provided by our dataset ScanEnts3D. Our main goal is to demonstrate the inherent value of the curated annotations of ScanEnts3D dataset. We try our proposed dataset ScanEnts3D on the following three tasks: neural listening, neural speaking or dense captioning, and 3D object localization. Our proposed modifications lead to substantial improvements in all the different architectures we tried. We therefore conjecture that similar modifications are or will be possible to extend and future architectures making use of ScanEnts3D dataset. For the neural listening, we propose three new loss functions. First one is the anchor prediction loss, which is responsible for predicting the anchor objects that are mentioned in the input utterance. The second one is cross-attention map loss, which operates on the cross-attention maps between the object features and the language features. And the third loss is the same class distractor prediction loss, which is responsible for predicting the objects that have the same class like the target object. We try these losses in two recent listening architectures, SAT and MVT. For the neural speaking task, we propose corresponding modifications and appropriate losses to two existing architectures. The first one is based on the SHOT and TEL model. The second one is based on the X-trans-to-cap model. We call our versions of these architectures SAT-cap ScanEnts and N2-cap ScanEnts. We proposed the M2CAP ScanEnts model, adopting X trans to cap model to operate with our proposed losses and modifications. The model is given a set of 3D objects in a 3D scene and outputs a caption for the target object. For example, the table shown here in the green box. The X trans to cap model exploits cross-model knowledge transfer, 3D inputs together with their counterpart 2D images, and adopts a student-teacher paradigm. Boxes in yellow show our modifications. First, we use a transfer learning approach by fine-tuning a pre-trained object encoder trained on the listening task to promote discriminative object feature presentations. And our modular loss guides the network to predict all the object instances mentioned in the ground truth caption. Our MVT ScanEnts neural listener, which is trained with our proposed dataset, and our auxiliary losses achieve state-of-the-art results, outperforming the current SOTA methods. MVT ScanEnts model outperforms the original MVT on both the NR3D and ScanRefer datasets by 4.3 and 5% respectively, while the SAT ScanEnts model similarly outperforms the original SAT model on both the NR3D and ScanRefer by 3.3 and 2.4% respectively. And for the neuro-speaking, the modified speaker models SAT-CAP ScanEnts and M2CAP ScanEnts improve significantly against their corresponding baselines. We observe that ScanEnts3D helps our speaker models to provide better captions for NR3D and ScanRefer across all the metrics. The M2CAP ScanEnts model improved the SOTA for neural speaking with NR3D per CIDR by 13.2 points. We investigate the extent to which our proposed dataset can improve the performance of different types of neural listeners. In particular, a widely used design proposed by ScanRefer benchmark requires a listener first to predict 3D object proposals and then identify the target proposals, which means it's a 3D object localization. To that end, we adopt the anchor prediction loss to work with the recent 3D JCG network. We see attained improvements in the 3D object localization performance when using our proposed dataset. Most importantly, we can observe an improvement in the more complex and harder cases, the multiple case. Here we present some key findings from our work. Neural listeners trained with ScanEnts3D are more context-aware than the models not trained with it. We conduct 3 additional experiments on both MVT and MVT ScanEnts neural listeners to verify such finding. The first experiment is to change the 3D input by removing the instances that corresponds to the anchor objects, basically remove the anchor objects. And the second experiment is to remove the words that correspond to the anchor objects and replace it with the unknown token. The third experiment is to provide a simplified scene by having only the anchor objects, the target object, and the same class distractor objects. We observed that removing the object proposals that correspond to the anchor objects from the input scene result in a massive drop in the listening performance in MVT ScanEnts. The drop in performance in MVT ScanEnts is much higher than the drop found in the original MVT model. The result suggests that the neural listeners trained with ScanEnts3D are similar to the humans, learn to heavily rely on the anchor objects to identify the target object, and are less influenced by the non-anchor or the non-mentioned objects. At the same time, we also observe an improved performance for MVT ScanEnts compared to MVT when providing as input a scene, a 3D scene consisting of only the target, its same class distractors, and the anchor object. We find that visual information about these anchors is both necessary and sufficient for the performance of our MVT ScanEnts model. Here we provide some qualitative results for our neural listener. Our proposed model MVT ScanEnts correctly predicts the target object shown in the green box, while the original MVT model fails in predicting the target object, where the wrong prediction is in red box. Neural listeners trained with ScanEnts3D dataset and with our losses have the ability to predict simultaneously the anchor objects, and the predictions of the anchor objects are shown in purple. Here we provide qualitative results for our neural speaker M2CAP ScanEnts compared to the original M2CAP model. Thank you for watching.